Welcome to NPTEL course on power system protection. We are continuing with transformer protection. We will go to details on differential relaying principle. In this lecture, we will address on percentage bias differential protection philosophy, and then we will proceed how a numerical does with different steps. We will have the initial portion on that. First step will be on normalization current, and the other steps you can say that we will elaborate more on subsequent lectures. So, in the last lecture we discussed on the differential protection and how the corresponding differential current is being processed in a in the protection scheme. So, if you remember, if this is the transformer, we have CTs in the primary side, here you can see that on the secondary side also. So, we have I and P, the line current flowing in the primary side, and I 2 P you can say that the line current flowing in the secondary side. We have CT connection, and then in the secondary side of the transformer we have I 2 S, and we have in the primary side the I 1 S. This current flows into the relay. Now, note you can say that how the corresponding CT is being connected, that is the CT polarity in both these sides, that matters. You can say that what will be the corresponding current through this differential branch. So, this R stands for here relay. Through the relay you can say that how much current will be sensed, you can say that depends upon essentially the corresponding polarity connections at the two ends of the transformer. Now, in this one, if you remember, you can say that for an internal fault, the corresponding current directions you can say that into the transformer being taken as the conventional current philosophy in this in the last lecture also. So, the corresponding differential current, otherwise called also the operating current, that becomes equals to I 1 S here this side and I 2 S this side, you can say that becomes. So, operating current becomes equals to I 1 S plus I 2 S. For an internal fault, both I 1 P and I 2 P will be these directions, and with you can say that CT polarity connections in this fashion, then the direction of current you can say that here, if this is entering here, so this should leave here. So, that is why the direction of current I 2 S, this is entering here. So, at this terminal this should leave here. So, direction of I 1 S is this. So, this philosophy, this results in you can say that I O P you can say that equals to I 1 S plus I 2 S. Now, come to a situation when an external fault or loading condition or so, then what happens here you can say that the direction of current you can say is flowing away from the transformer in the secondary side. So, therefore, with the same polarity of connection you can say that what we have seen in the earlier one, then what will happen you can say that in this case the current being reversed as compared to that, the corresponding current in the CT also reversed. So, that is why the direction of you can say that I 2 S will be in this way. The primary current you can say that remaining same, incoming current here in this direction. So, with this CT polarity, the corresponding current direction will be leaving to this terminal. So, I 1 S remain same as earlier case. That results in you can say that the corresponding I 1 S and this corresponding I 2 S. So, I 1 S flows here and I 2 S leaves here. So, therefore, the differential current becomes equals to I 1 S plus minus of I 2 S, and if these I 1 S and I 2 S are same, because assuming you can say that the correct value of the CT you can say that available, then this current you can say that will be ideally 0. So, this is what the corresponding philosophy being can say that being used you can say that in the for the transformer differential current perspective. So, we can say that we see that differential relay operates you can say that on the sum of the currents entering to the protected element, and that we term as a differential current. The differential current at the CT secondary level is proportional to the fault current for the internal faults, and approaches 0 for any other operating condition. So, what we mean to here is see here. So, this for this internal fault, let us say x amount of current flows here. So, then I 1 p and I 2 p, I 1 p plus I 2 p will be the x, and then you can say that in a similar that issue. So, these I 1 s and I 2 s are proportional to I 1 p and I 2 p. So, therefore, you can say that the corresponding I O p will be proportional to the x amount of current depending upon the CT ratio and so. So, that is what we say that the operating current here for the internal fault I 1 plus I 2 s is proportional to the amount of fault current in the internal fault current in the transformer. Note, in literature you will find, you can say that while studying that there is another convention also used, you can say that you will find in the literature. If the CT polarity you can say that change here, then this you can say that one side only, you see here one side of the CT polarity is change, then what happens that the corresponding you can say that sign convention which we have used I 1 plus I 2 s, that becomes equals to I 1 minus I 2 s, agree. So, that you can say that the only difference we will find. So, many you can say that books and literature you can say that go for that kind of approach, but that does not conflict to the protection philosophy in general. However, the approach which you have described here you can say that will follow throughout, you can say that is I operating becomes equals to I 1 s plus I 2 s. Now, we know that for any internal fault the I 1 s and I 2 s will be, you can say that summation of this will be proportional to internal fault. That means that the differential current or the operating current will be significantly high for an internal fault in this arrangement. So, if you can say that simply adjust the amount of current in this branch, then the corresponding protection scheme can identify that this is an internal fault. For any external fault, this current becomes I 1 plus or minus of I 2 s, that becomes close to 0. So, therefore, the corresponding current to this differential branch will be significantly low or near ideally 0. So, by an overcurrent principle, we can discriminate whether the fault is internal to the transformer or external or a normal loading condition or so. So, that is why I can say that we can think of an overcurrent principle, you can say that for this you can say that differential applications with available currents from the CT as shown here, and the connection becomes as we have followed in this diagram. Now, however, the problem with that, there are numerous you can say that problems you can say that applying overcurrent principle in this you can say that for the differential current branch. Number one, you can say that transformer has magnetizing current. See, if that you can say that flows only primary side, will not flow in the secondary side. That means that there is an additional current you can say that to the transformer in the primary side. So, that current you can say that will be additional current and that will flow you can say that this one. So, that is the spill current flowing to the differential branch. In addition to that, if any CT ratio mismatch happens to be there, which we have already calculated in the earlier lecture, then what happens that even though there is no fault, or you can say that for external fault situation, the corresponding you can say that differential current will be again there because of the mismatch in CT. So, these are not fault situation, internal fault situation, but still you can say that differential current will be flowing, and that may be significant. You can say that if the fault happens to be external and very large amount of current in case of a CT ratio mismatch. We know during the CT performance study that CT may saturate, and thereby you can say that what will happen, the corresponding current may be substantially low. So, for an external fault, if any of the you can say that CTs will saturate. So, even though it is you can say that external fault, I am say that at that time also differential current will flow. So, therefore, the overcurrent you can say that relay will be unable to discriminate whether it is internal fault or external fault in those kind of situation, and therefore, if we think about applying a simple overcurrent link principle here, that may find limitation in overall performance while protecting a transformer. if you try to compensate all these errors, then you can say that the pickup current, you can say that which will fix for the overcurrent length will be very large, and therefore, you can say that if the pickup current becomes very large, you can say that then you can say that the dependency, you can say that dependability issue will be compromised in general. So, therefore, alternative you can say that ways are being sought, and we will go you can say that on that perspective. The solution to that, if you see the different literatures and available relaying you can say that principle in this, most you can say that of the relays use percentage bias differential protection in a numerical platform. So, we see you can say that these relays offer sensitive differential protections even at low currents and tolerate larger mismatch at high currents also during CT saturations, or you can say that and other like magnetic inrush and over excitation situations issues also which the overcurrent relay find challenges. So, what is being done here? For this you can say that these kind of connections and all these things, we have this you can say that the relay characteristic very basic one we are going for, then we will go for the further details on this, that the differential current versus the corresponding restraining current. Agree? This restraining current is nothing but you can say that they related to you can say that more current in these you can say that through these two cities, then you can say that the corresponding oppositions maybe oppositions you can say that the to the you can say that operating current will be more and more. The philosophy behind this is that whenever you can say that the corresponding through current external fault current, the amount of current becomes much higher, and then you can say that let us say one situation we consider CT ratio mismatch. If the CT ratio mismatch is there and the current for an external fault the current becomes very large, because of the CT ratio mismatch the amount of current you can say that which will be flowing through this branch is also larger. So, that is not an internal fault situation. To overcome that problem you can say that it means that for large current you can say that external current or large current through these cities, you can say that the restraint should be more also, and that is what in this protection philosophy it is being provided that if you have you can say that large current you can say that in these cities, then the restraint should be more, and thereby you can say that the relay can perform better way. So, what we have shown you can say that here that the corresponding you can say that we have a slope here, and this slope you can say that maintains that you can say that approach you can say that what we talk about the distance. What is that restraint current you can say that, and where how much you can say that the corresponding slope should be taken care and all these things. Rest of the details you can say that we will have in the next subsequent slides. Note here you can say that we have some spill current always in this you can say that branch like magnetizing current and so, or the any CT ratio mismatch, and you can say that that amount you can say that. So, therefore, you can say that we have a minimum pickup current minimum current setting that we call the pickup current setting you can say that. So, in this environment situation the trip condition for the differential will be if the I operating is greater than IPU, that is pickup current, and then you can say that the I operating you can say that greater than MM IRAS you can say that in this region of perspective, and so whenever the corresponding operating current is greater than you can say that this you can say that threshold value, above this you can say that it is a trip you can say that region, otherwise you can say that at distance it remains silent. Now, you can say that we will elaborate more on you can say that this perspective you can say that what are these I operating, what the restraint you can say that currents and so on the percentage bias differential relay principle. So, this I operating here is that differential current to this you can say that branch, or you can say that the in a numerical relay you can say that the corresponding I 1s plus I 2s what we have already elaborated on. So, the differential current which is the phasor or instantaneous value, it can be both. Some relays most of the relays use phasor values, and many relays can say that they exploit the advantage of high speed protection using instantaneous values also. So, flowing into the zone of protections. So, flowing into the zone of protection is the transformer here, and so you can say that. So, here you can say that whatever you can say that current flows into that, with that considerations the operating current or the differential current is I 1s plus I 2s, which we have already discussed, and this principle will follow in our approach. The I restraining current is in this you can say that percentage bias relay characteristics is the measure of the current flowing through the zone of protections. It is a measure of the current flowing through the zone. We mentioned that the big challenge you can say that CT ratio mismatch, CT saturation and so. So, for that you can say that we say that whatever current is flowing through this zone. So, it is a measure of that, which one? The restraint current. This provides the desirable feature for restraining the relay, but not allowing the relay to operate when high levels of current flowing through the zone. So, the relay serves you can say the differential protection is vulnerable, as we have mentioned earlier, that whenever the fault happens to be external to that, and because of some CT ratio mismatch or so, the spill current or the differential current will be significant, and to avoid that you can say that the restraining current approach is provided, and but we say that the more the corresponding through current in the both the CTs, the more you can say that restraint is required. So, that the relay does not operate for that external fault or any other conditions. So, for this you can say that if you see the literature, manufacturers provide you can say that generally 3 you can say that approaches for computing the I restraint. K is a factor, and the modulus of you can say that I 1 s minus I 2 s, differential current is I 1 plus I 2 s, and restraint current is I 1 s minus I 2 s, mod of that into K. There is another approach of computing the I restraints K into mod of I 1 s plus mod of I 2 s, the magnitude of current of both primary side and the secondary side you can say that of the transformer. The other one you can say that maximum of I 1 s or I 2 s. Agree? So, these are the common you can say that restraining currents which is being used you can say that on this percentage bias relay characteristics with k equals to 0.5 or 1 you can say that in these relations, most of the relays you can say that use k 0.5, k 0.5 is a very popular value. When high currents are present, it is more likely that the CT may also saturate, and then you can say that a false you can say that differential current may flow, which we have already mentioned. So, this you can say that may lead to you can say that operation of you can say that the relay unwanted maloperation. So, to avoid you can say that when the corresponding current happens to be the large you can say that then this happens to be there. So, therefore, you can say that we the mechanism has to you can say that take care that perspective and all these things. So, that is what we say here. So, we essentially require a characteristics a higher percentage of differential current to operate a higher level of through current. It means that when through current is means external through current is large. So, essentially we require you can say that a higher differential current, and that is the reason you can say that we keep a slope here for this region you can say that, and that you can say that mitigates or provides a way to overcome this problem. Now, that we discuss is of 2 winding transformer, 3 winding transformer, like you can say that a delta winding is maybe a third winding option, and so in many applications in high voltage system and so or power transformer. So, in that case you can say that I 1 s entering, I 2 s entering, and for the third winding I 3 s entering. So, all 3 currents are entering to the zones, that is what the philosophy we are considering in our approach. So, in that case the operating current is earlier it was I 1 plus I 2 s, now we consider we have added I 3 s. So, the magnitude of that current is our operating current. Restraining current we consider earlier I 1 s minus I 2 s, now we can say that we are subtracting minus I 3 s also, and now we can say that we are having another restraining that becomes equals to minus I 1 s plus I 2 s minus I 3 s. This you can say that the other restraining you can say that is required in case you can say that the corresponding primary side breaker is open, and you can say that we are feeding from only from the secondary side. So, that means you can say that the corresponding I 1 s may reverse you can say that from that perspective. So, that is why I can say that the second restraint current is necessary to protect the transformer operating when the primary breaker is open, one side breaker is open in that perspective now these things. So, these are being say that different restraining and operating currents being considered for 2 winding and 3 winding transformers to have the required percentage bias settings. Now, we will having the more details on the percentage bias differential relay. So, we are going more details into that, and in the subsequent lectures also we will clarify on different perspective and issues related to differential relay operation with using percentage biased principle. Note, the percentage differential characteristics can be fixed or variable based on the relay design. That flexibility there in today's you can say that numerical link principle. There is also a minimum differential current threshold before tripping without regard to the restraint current. So, that is a check that there must be at least minimum you can say differential current. You can think about this I pickup current and so. Details of minimum pickup current, restraint current, characteristic flows vary among manufacturers. So, here PC you can say the characteristics you can say that we have pickup current and the different slopes and all these things. So, that vary with the manufacturers. Slope may not be one slope as you have earlier shown with one slope m or so. Slope can be two slopes m 1 and m 2. Now, we have you can say that a different slope here, the reason behind already you can say that we mentioned that during higher level you can say that current level you can say that the chance of you can say that the differential current may be much more, having larger value of you can say that differential current, either you can say that due to CT ratio issues or you can say that or the more prominent you can say that possibility of more you can say that CT saturation issue. So, these you can say that curves allow the percentage mismatch during large currents also. It is not necessary you can say that some of the you can say that relay use you can say that a curve also you can say that for this perspective also instead of two slopes of m 1 and m 2. Now, note that how to decide this m 1 and m 2 or this you can say that characteristic above which you can say that it trip and below which you can say that it is the restraint region. So, for this you can say that let us you can say that to start from this very basic one, the magnetizing current. So, we have this magnetizing current 2% or so you can say that for a transformer. We say CT ratio mismatch, let us consider CT ratio mismatch you can say that it means that more current you can say that through the two CTs means the corresponding differential current becomes more. So, that is why I can say that CT ratio mismatch leads to you can say that also the corresponding the differential current, unwanted differential current more and more for the with larger value of through current. Through current larger means restraining current also becomes larger. So, that is why the line becomes like this. In addition to that, the tape changing transformer, remember you can say that many transformer, most of the transformers rather in power transformer, they have the you can say that tape changers. So, that tape changers you can say that we have, then the turns ratio you can say that of the transformer N 1 is to N 2, capital N 1 is to N 2 change, and then you can say that again you can say that the corresponding differential current will be more prominent. So, therefore, if the corresponding loading condition is higher and higher means restraining current is higher, then with tape changing position changing that the corresponding differential current may be more and more, but that is not an internal fault situation. Furthermore, we know you can say that CT has limited performance, you can say that when the current becomes significantly high because of the CT saturation issue. So, therefore, you can say that we expect you can say that very large you can say that false current in the differential branch due to CT saturation perspective, and this you can say that is a curve like this. Now, when we add all you can say that these you can say that perspective and so, then the total may can say that sum up you can say that we can say that the false current that we are saying in the differential branch may be considered as the green curve like this. So, this is about the adding all you can say that perspective and so. So, having some margin above you can say that this, so that you can say that the decision can be more secure, unwanted tripping can be avoided, then we set a curve you can say that like this you can say that for the differential percentage by differential characteristics. And on that you can say that as already mentioned, we can many relays you can say that put two slopes m 1 and m 2, and this m 2 slope is much higher, then you can say that this m 1 typically m 1 can be 0.2 to 0.3 kind of thing, and m 2 can be can say that much larger you can say that as high as 0.5, 0.5 or so also. I would to mention also clearly that the reason behind you can say that the larger value you can say that of that one go for the more mismatch, more differential current, and also CT saturation creates further problem. So, to avoid you can say that kind of things you can say we have there you can say that this kind of m 1 m 2 becomes the m 2 becomes larger than the m 1. Furthermore, you can say that depending upon situations, we will see elaborate more on that. This can be considered also adaptive, this you can say that portion can be adaptive. Sometimes you can make it more and sometimes you can make it higher depending upon to have the considered required security or dependability, have better accurate protection approach and so on. The pickup you can say that value you can say that it decided you can say that what is the spill current flowing through this you can say that because of this CT ratio mismatch, the magnetizing current and so, and this is the considered minimum current above which you can say that the trip options can be triggered we can say that, and then we say that anything you can say that above the consider this curve you can say that is a trip you can say that decision, and below this is the restraint you can say that option. Now, while going for you can say that the settings and all these things, how to you can say that some of the you can say that literature suggests you can say that if this is the pickup current you can say that, then we go for you can say that the slope fast slope you can say that this line you can say that passes to the origin and then it goes to consider that up to this point. This point you can say that is nothing but this the second pickup level, and the second pickup level you can say is decided by this fifth harmonic restraint being provided in the for the percentage by this relay you can say that is for you can say that the over excitation phenomena when voltage becomes higher. So, this will address you can say that in the subsequent lectures to clarify that perspective and all these things, that what is the you can say that fifth harmonic restraint and so, and how that is being set in a numerical relay. And then you can say that begins the you can say that the high slope you can say that region about the M2 and so, and this is what you can say that the corresponding percentage bias you can say that characteristic is being set for a relay in a numerical relaying platform. Now, let us go to examples. This is the 9 bus systems, and we have considered this for a 50 Hz system 220 kV level of voltage. We have considered a transformer in this source side 11:220 kV 50 MVA capacity, and we have now star grounded delta Y connections. So, the vector group is YD1 connection and all these things. Agree? So, we will have you can say that with this transformer connection can be different, that also will elaborate in the subsequent slides also. Now, let us you can say that for this transformer which we have mentioned in the earlier slide. So, this is the transformer connection, high voltage side star, 11 kV side, delta low voltage side. Now, in the last lecture we talk about you can say that how to fix the CT, that is the first step of the protection, because the differential current which will be calculating and which will be analyzed by the relay is based on you can say that the current provided by the CTs. And note that you can say that we have already mentioned that numerical relay you can say that use the corresponding CT, both the sides you can say that CT to be connected in star. So, both the CTs are set of CTs are you can say that connected in the star. So, with that you can say that what will be the corresponding CT ratio selection choice, we will see first that perspective. We will fix the CT ratio and then proceed for the further protection in the percentage by relay perspective. So, for this you can say that transformer rated current on the low voltage side and the high voltage side. So, in the primary you can say that high voltage side. So, we find to you can say that 131 ampere, 50 kVA to 50 MVA to 20 kVA. So, this gives you can say that 131 ampere. Low voltage side system side current, this becomes 2624 ampere. These are the two rated currents, high voltage and low voltage respectively. Now, as I already mentioned, some you can say that utilities follow 125% of the corresponding current rating for the CT selection. So, this list you can say that 125% of this low voltage is 3280 ampere. So, CT selection is based on the availability 3500:5. Now, when this transformer is carrying its rated current, full load current, the CT secondary current becomes equals to, this is the full load current divided by the CT ratio, that becomes 3.75 ampere. So, this is what 3.75 ampere when this amount of current is flowing in the CT, and if you have finalized the CT to be 3500:7. In that situation, ideally the secondary this side current, the high voltage side current also should be considered 3.75 ampere. So, our CT selection should be such that the current from this side also should be same amount of current, so that the differential current becomes 0, and this is what the normal situation, and then we say that yes, our selection of CT is ideal, justified. With that, you can say that thing, considering this same amount of current from this side, if we calculate, so that is why this 131 ampere the full load current which will be flowing in the primary divided by the 3.75 ampere which is expected in this side of the secondary of the CT, and this is a 5 ampere CT. So, then we can say that we got it to be 174 ampere, agree, we got to consider the corresponding 174 ampere that corresponds to your CT ratio. So, how do you get this one? 131 is to, suppose x is to 5 is the CT ratio for this side, which will give you 3.75. So, that is why we are trying to find out what is the x value. So, that x value becomes this 174. So, therefore, this should be 174 is to 5, but that 174 is to 5 CT is not available. So, we are going to consider a nearby CT that becomes equals to 200 is to 5, 200 is to 5. So, our final CT selection you can say that from the low voltage side is 3500 is to 5, and the primary side you can say that it becomes 200 is to 5. So, there is some mismatch you can say that we expect now, because we could not find 174 is to 5 ampere CT, and that you can say that if we calculate that becomes equals to, you can say that the with that current 131 you can say that ampere this side primary current with 200 to 5, this becomes 3.3 ampere, but this side current is 3.75 ampere. So, there is a difference of current, even though you can say that it is not a fault, it is a normal situation, normal loading condition, and that with difference is 3.75 minus 3.3. So, that you can say that each current divided by 3.75 leads to 12% error kind of thing in this arrangement. And why this error? Only due to CT ratio mismatch, only due to CT ratio mismatch. Now, in numerical relay we have enormous scope to consider, to calculate, to compensate, and to in real time you can say that calculation and so and so. So, before going to you can say that details of you can say that how the things are being processed for the percentage by differential relay principle in numerical relay, we will have you can say that terminology called current normalizations. So, for this why we are doing this, unless you can say that you handle the current properly, then the differential current will be unwantedly you can say that will be very large, and then the relay may malfunction. So, and the accuracy in terms of dependability and security, the reliability perspective will be considered will be poor, unless you can say that we can handle the currents properly. So, the what is being done in normalization of the current, you see you can say that the primary side normalizations that becomes equals to CT ratio of that side, CT ratio 1 the primary side divided by I 1 rated into I 1 s. The normalized current is I 1 s, the secondary current in the primary side of the transformer, into the CT ratio divided by the rated current, divided by the rated current. So, the secondary current into CT ratio should we give you this primary side current of the system divided by the rated current. So, that is you can say that the normalized current you can say that on the high voltage side or the primary side. Similarly, in the second you can say that side also, in the of the secondary side also you can say that we can have this corresponding I 2 s in that side into the CT ratio, corresponding CT ratio divided by the rated current. So, this is about the normalized current. Now, let us see the consider the example which we have considered for the 9 bus system, where we have the transformer 50 MVA transformer. For that what happens to there, and note that you can say that the corresponding conventions which we are using you can say that already mentioned, it is like this you can say that for this kind of CT polarity connections. High voltage CT we have considered fixed you can say that 200 is to 5, and the rated current we have already found out is 131 ampere. So, the I normalized current becomes equals to this I 1 s you can say that we have seen 3.3 ampere, CT ratio you can say that 200 is to 5 is 40, and the rated current is 131 ampere. You remember this 3.3 ampere we have found out, you can say that during that rated current perspective. So, this gives you can say that 1 ampere normal edge current. Now, low voltage side CT we have selected is 3500:5 and the rated current is 2624. We have already calculated for the transformer star grounded delta YD1 connection. The normalized current in the secondary considered CT ratio 2, I2 considered I2S we have 3.75, we have already found out. CT ratio this gives you 700, rated current is 2624, so this gives 1 ampere. Now, what we see from this you can say that if you can say that normalize the current, even though we have not got the proper CT ratio as we have already discussed in the earlier slide, if we normalize the current for these situations we are getting 1 ampere this side, 1 ampere this side. So, if we use this you can say that for normal situations this will lead to 0 differential current. So, that is a better thing than the 12% error which you calculated in the earlier slide for the corresponding field current. So, that you can say that the advantage you can say that to exploit the advantage you can say that by normalizing the current the way you can say that we did here. Now, we have you can say that tape changing transformer and so, and that creates problem you can say that in this perspective also, that may also lead to consider that the unwanted false current in the differential branch. Now, tape changing transformer is a common thing in high voltage system applications. Two options in tape changing transformer, one is no load tape changer that goes as high as 5% tape changing to make the change the corresponding voltage generally provided in the high voltage side. Now, the point is that this is at no load. So, if already you can say that the corresponding tape changing is done and that is being accommodated in the setting N1 is to N2 and accordingly you can say that the corresponding rated current and so calculated and taken care in this setting, no problem. If it is not taken care, then the differential current will be there. If differential current will be there, you can say that for normal situation also, then the pickup current has to be more or the corresponding M1 slope has to be more, that has to be addressed you can say that properly, otherwise there will be false trip in the system. Unload tape changers. So, this you can say that the it is more challenging. The unload tape changers means you can say that during different situations in operation of the system, the tape changing transformer the tape position changes and thereby you can say that the corresponding differential current is expected to be high even though it is no fault or so. Now, numerical relay today has the ability to adapt the situations, calculate the corresponding tape changing situation and again you can say that adjust the corresponding normalized calculation and so including the CT ratio and it can you can say that lead to you can say that minimization of you can say that the corresponding spill current in the system. Now, if it is not that so, these you can say that tape changing transformer can be as high as you can say that plus minus 10%. So, then if that kind of you can say that adjustment is not there in the numerical relay, then the corresponding associated you can say that the mismatch you can say that which happens to which will happen you can say that with this one will be of significant nature and that must be considered included in the corresponding percentage bias relay characteristic setting. The slope is in the important factor for this perspective and so, because 10% is not a small value, it is of significant value. So, therefore, this corresponding M1 and M2 are to be adjusted accordingly. Now, come to different transformer connections, how do affect the relaying perspective in the percentage biased relaying applications. Let us say you can say simple one star star or similarly delta delta also. So, we know they do not have any phase difference, we consider y 0 degree phase difference. So, we say can say that this is the system side current, high voltage side is capital Y, capital A corresponds to high voltage side, small a corresponds to low voltage side. Both are having star grounded. So, this is the primary current and this is the loading condition current flowing this one. So, the system current for this one, agree, for system current no issue of protection we are discussing. The per unit current you can say that IAP and this IAP low voltage side current, they align you can say that with 0 degree difference, agree. And if we talk about the per unit current, normal edge current, so that becomes the same magnitude. Now, let us come to the protection of such a transformer. So, now we connect the CTs as we have already defined, already you can say that mentioned that with proper polarity connections and all these things. So, with CT connections we mark you can say that the current flow is in zone towards the zone. So, now you can say that the corresponding for this case normal situations, the corresponding this current will be reversed. So, when you go to the normal edge current means that the CT secondary current and you divide and multiply that factors which you have already considered in the earlier example. For this you can say that I operating current to be I 1 s plus I 2 s principal. Then we say that for this you can say that situation normal situation, the I A n you can say that I n will be in phase opposition with this kind of CT connections which we have discussed. So, they will be 180 degree. And for internal fault, when the fault becomes internal, this is for normal flow condition, and when the corresponding current becomes internal, the current you can say that will be the right hand side current will be out of phase you can say as compared to this. So, they will be aligned to 0 degree. And now, if we take the operating current to be I 1 plus I 2 s, so these two will be added. So, differential current will be significant for internal fault. So, that is what we say in terms of this, agree, that is what the desirable, and that you can say that is that for internal fault this becomes 0 degree, for you can say that for external fault you can say that this becomes 180 degree. Now, come to YD1 connection for this transformer. So, we know high voltage leads the low voltage by 30 degree. So, per unit current. So, the high voltage current leads you can say the low voltage current by 30 degree. When you come to the CT connections as we have already defined. So, the normalized current after the scaling down as we have done in that earlier example. So, this current will be reversed. So, therefore, what happens that if we consider you can say that these currents to be reversed. So, this you can say that I A n this side current will be reversed after the CT connection. So, this is about the CT secondary we are looking at. So, with respect to the you can say that the high voltage side current, the corresponding you can say that the low voltage current will be making an angle of 150 degree, and this is in the CT secondary side for normal or external fault condition. But for internal fault conditions, the current direction will be reversed to that, and then you can say that will be it will making 30 degree to the high voltage side current, agree. So, this is what you can say that we see here. But note that you can say that our objective you can say that I operating to be I 1 plus I 2 s. So, it means that these you can say that the low voltage side current should be aligned you can say that in the direction of you can say that the high voltage side, means that these 30 degree has to be compensated for that perspective. So, that is what the requirement you can say that the phase has to be compensated in case of a YD1 connection or so. Now, go to the DY1, high voltage side is delta and then DY. So, high voltage side leads you can say that the corresponding low voltage side by 30 degree. This is what the connection says. So, system side current similar to what we have discussed earlier. Now, come to you can say that with CT connected and in the CT secondary side current, normalized current. So, 30 degree leads this here. So, because of the CT connections this will be reversed. So, therefore, you can say that to the primary voltage, high voltage, the high voltage side, the low voltage side we can say that having and making angle of 150 degree, and this is for you can say that external for any loading condition, normal loading condition. But for internal fault you can say that again it will be making 30 degree. So, like earlier case, this phase angle you can say that has to be compensated. So, that the small I and you can say that this you can say that will be aligned to this the high voltage current phasors. So, coming to you can say that two applications for that 9 volt system and transformer, we see you can say that now. suppose an internal fault, you can say that phase A to ground fault is being created at 1 second, and then we see, you can say that the corresponding phasors, you can say that the normal edge current, secondary current in the cities, you can say that which you have selected, you can say that for the high voltage and low voltage side. So, this is you can say that the star grounded you can say that transformers with this convention of city connections. And so, now you see, you can say that for an internal fault case, this is an internal fault case. So, we have both, you can say that normal edge current and primary and secondary side, blue is for the high voltage side, and the red you can say is for the low voltage side. We consider in our throughout discussions one, that is primary, or so we can say that one side is the high voltage side, two is the low voltage side, that is the convention we will be using throughout. So, you see, you can say that during normal conditions they are out of phase 180 degree, and during internal fault situations phase angle is 0. So, these additive things makes the operating current to be significant, and the subtractive things makes the operating current to be negligible, and that is what desirable also, that the differential current you can say that during normal situation should be 0 ideally, but during internal fault situation of this region, this should be, the differential current should be significant, and this phasor you can say that gives us that one. So, in this case we say that you can say that we do not require any, you can say that phase compensation also, what we mentioned earlier for the star grounded situations with 0 degree phase difference between primary and the secondary. Now, come to you can say that where I am say that the Y grounded you can say that D1 connections of the transformer, same situation fault, internal fault you can say that phase A to ground you can say that in this system, and then you see primary side to be you can say that here for this case, because of the you can say that the YDY connections, the angle becomes 150 degree, and for internal fault case you can say that the angle becomes 30 degree, which we have already discussed earlier. So, therefore, what we essentially need you can say that to have you can say that operating current significant on aligned with the corresponding low voltage current can be aligned to the high voltage current perspective, we need to consider angle compensation here. Now, for the DY1 connection similarly, we found the corresponding current you can say that and voltage to be this, again same 150 degree and 30 degree. So, here also you can say that we need to consider angle compensation to be there. Typically, these kind of angle compensation is being done in earlier version of you can say that analog relay also you can say that by connecting the cities in star and delta you can say that for a delta star transformer, and that you can say being there, but now you can say numerically that is not being done. So, all you can say that the phase compensation is being done in the numerical calculation perspective. How that is being considered done for the different vector group you can say that transformers and all these things, we will clarify more on next you can say that lecture on that perspective. So, in overall in this lecture we say that percentage bias you can say that differential principle is a good solution you can say that for transformer protections to address CT mismatch, transformer tape changing transformer issue, CT saturation and other you can say that challenges in terms of that. For correct decision using difference principle you can say that the phase shifting you can say that perspective has to be addressed you can say that for different vector group transformer, and that must be addressed you can say that properly, that we learn from the examples and phasor diagram. The compensation techniques for the you can say that will be considered in our address in next lecture, that I already mentioned. In addition to that, zero sequence current flows in the star grounded side, not in delta side, that also you can say that is to be addressed you can say that, which we will see in the next lecture in more details. Thank you.